What specific problem does the loss-to-loss prediction method aim to solve, and how does it address the limitations of existing scaling laws?
The loss-to-loss prediction method aims to solve the problem of predicting model performance across different data distributions, particularly in the context of transfer learning. Existing scaling laws are distribution-dependent and primarily focus on training loss, which limits their applicability when transitioning to new datasets. By establishing a methodology that predicts the loss on one distribution from the loss on another, loss-to-loss prediction allows for the translation of scaling laws from a source dataset to a target dataset, thereby enhancing the ability to forecast performance on new tasks. This approach addresses the limitations of existing scaling laws by enabling practitioners to leverage data from multiple pre-training datasets, leading to better predictions with fewer training runs on the new dataset. Ultimately, it provides a more robust framework for understanding how scaling laws change across datasets and improves the efficiency of model training and evaluation.
How does the proposed loss-to-loss prediction methodology work? Illustrate the step-by-step process and any novel components involved in making predictions across different data distributions.
The proposed loss-to-loss prediction methodology operates by establishing relationships between losses calculated on different data distributions, specifically through three main types of predictions: train-to-train, train-to-test, and test-to-test. First, for train-to-train prediction, the methodology fits a shifted power law relationship between training losses from models trained on two different datasets, allowing for the translation of scaling laws from one dataset to another. Second, in train-to-test prediction, the methodology predicts the test loss on a target dataset based on the training loss from a source dataset, utilizing the irreducible error from the scaling law fit on the source dataset. Lastly, test-to-test prediction generalizes this by comparing test losses across models trained on different datasets, enabling predictions about performance on a new test distribution based on known test losses from a source distribution. A novel component of this methodology is the ability to leverage existing scaling laws and model performance data from one dataset to enhance predictions for another, thereby improving efficiency and accuracy in estimating model performance across diverse datasets.
Can you present a simple yet illustrative example to demonstrate the inner workings of the loss-to-loss prediction? Walk through the main algorithm steps with specific loss values and datasets.
To illustrate the loss-to-loss prediction, consider two datasets, P_0 FineWeb and P_1 StarCoder. Suppose we have trained a model on P_0 and obtained a training loss L_0 equals 0. 5. We want to predict the loss on P_1. According to the train-to-train prediction methodology, we fit a scaling relationship between the training losses of models trained on both datasets. For instance, if we find a shifted power law relationship characterized by parameters k equals 1, 2 and kappa equals 0, 9, we can express the relationship as L_1 equals k CDOT L_0 caret kappa. Plugging in our values, we calculate L_1 equals 1, 2 CDOT 0.5 caret 0.9, approximately 0.76. This predicted loss on P_1 indicates how the model's performance might transfer from the training distribution of FineWeb to the coding tasks in StarCoder, demonstrating the practical utility of loss-to-loss prediction in understanding and optimizing model performance across different datasets.
What are the practical and theoretical benefits of applying the loss-to-loss prediction method? How do these benefits compare with traditional methods of scaling laws?
The loss-to-loss prediction method offers significant practical benefits by enabling efficient scaling law fits across different datasets, allowing practitioners to leverage existing models trained on one dataset to predict performance on another with minimal additional training. This approach can yield better predictions with as few as 8 models on the new dataset, outperforming traditional independent scaling laws that require fitting new models from scratch. Theoretically, it provides insights into how scaling laws vary across datasets and enhances our understanding of transfer learning dynamics, as it captures the relationships between training and testing losses more effectively than conventional methods. Additionally, loss-to-loss prediction can help identify optimal model sizes invariant to data distribution changes, a feature not typically accounted for in traditional scaling law approaches. Overall, this method not only improves prediction accuracy, but also deepens our understanding of the underlying mechanisms of model performance across diverse data distributions.
How does the study validate the proposed method? Discuss the experimental design, datasets used, and the benchmarks or metrics that demonstrate the effectiveness of the loss-to-loss prediction methodology.
The study validates the proposed loss-to-loss prediction methodology through a comprehensive experimental design involving 6 diverse pre-training datasets: FineWeb, FineWeb-Ado, ProofPile2, SlimPajama, SmolLM Corpus, and StarCoder v1. The authors trained a total of 528 models across these datasets, varying model sizes and flop budgets, to establish a robust framework for comparing training and test losses. They employed 3 types of loss-to-loss relationships: train-to-train, train-to-test, and test-to-test, demonstrating that a shifted power law effectively captures the scaling relationships between losses across different datasets. The effectiveness of the methodology is further supported by empirical results showing that predictions made using loss-to-loss relationships yield better scaling law fits and test performance predictions than independent scaling laws, particularly when only a small number of models are trained on a new dataset. Metrics such as cross-entropy loss on downstream tasks serve as benchmarks, illustrating the practical utility of the proposed method in predicting performance on unseen data distributions.
What were the key results achieved through the loss-to-loss predictions? Provide specific data points that highlight the performance improvements or unique insights gained from this method.
The key results achieved through loss-to-loss predictions include the identification of shifted power law relationships across different datasets, which allows for effective predictions of training and test losses. Specifically, the train-to-train predictions demonstrated that by fitting just 2 parameters, K and kappa, one can capture the scaling relationship between training losses across datasets, yielding better predictions with as few as 8 models trained on a new dataset. In the test-to-test predictions, the method showed that the asymptotic transfer performance on test sets could be significantly worse than direct training on those datasets, emphasizing the importance of including diverse training data. Additionally, the results indicated that leveraging existing models from a source dataset, e.g., FineWeb, to predict performance on a new dataset, e.g., StarCoder, could yield predictions nearly matching those obtained from a full set of models trained on the new dataset, with an R-squared value close to 0.001 compared to the baseline. Overall, these findings highlight the practical value of loss-to-loss predictions in improving model performance and understanding transfer learning dynamics.